Okay, so thank you, Maya, for your introduction. So thank you, everyone, for being here. I know it's kind of late, especially in Europe, so I'm going to try to be brief. And as you can see, I don't have that many slides, only 26. So if you have any questions, feel free to ask them during the talk. I'll be happy to answer them. So yes, I'm going to talk about fundamental diagrams. So it's something we already have seen many times during the workshop. And here I'm going to talk more from like an interdisciplinary point of view. So I'm going to try to kind of link this fundamental diagram with several type of experiments that my collaborator did. So for two type of biological system, pedestrian and ants, and we're going to try to use fundamental diagram more like as a tool rather than saying that that's the model. It's just going to be a way to explore what's going on. Okay, so let me just give you like a brief outline. So I'm just going to do like a quick introduction. So it's going to be brief because, as I said, many people already talk about fundamental diagrams, so I don't need to spend too much time on this. And then basically just two parts, pedestrian first, and then we're going to move to ants. So fundamental diagram, we've already seen this picture here, this function. So we try to explain how the flux related to the density, and there is a very first elementary model describing what's going on if you try to just put that in your model. And I refer here to the talk of Rinaldo Colombo. We really give you a great overview about all the literature, etc. So just two things here. So we have basically two phases. So we have first a phase where it's a free flow. So just a flux increase linearly with the density, and it starts to be congested. And when density is too large, then you have a traffic jam. So, of course, especially for this workshop, what would be the goal here is if you want to apply this for autonomous vehicle, you will try to kind of improve this curve. So we try to get above and also try to mitigate, so try to avoid this traffic jam occurring. So here, I'm not going to spend too much time on this. What I'm going to try to go over instead, I'm going to try to see what is this fundamental diagram or or how it looks like for different type of organism. So two things here. So once again, pedestrian and ants. And there's a key difference compared to car traffic is that whether you like pedestrian or ants, there is no predefined road. So you not necessarily, even if it's a corridor, you don't say you have to walk this way. It's always more like 2D or pseudo 2D. And so there is some lane formation. So it's more complex, let's say. And for those who haven't seen, I encourage everyone to go to see the talk of Ted, who discuss about this kind of lane formation in ants. So let's, with this, let me just go kind of a methodology and overview about how we try to model things. So we're gonna have basically two steps. So first, we have to do some experiment because instead of it's not a physical system, so we need to kind of come up with your experiment to try to see how things going on. There's no fundamental law or Newton law. You have to find those. And usually what we do, we try to track individual agents or pedestrian or ants to try to infer what are the rules, how do they behave. And with that, when you're at this level, then you try to derive what's happening at the macroscopic level. Here is going to be a little bit different because we it's just going to be traffic. So we're going to almost skip this step of going to agent-based model. What we're going to do directly is try to link experiments with macroscopic model. And we can do that here because it's almost, I'm going to discuss more about that, it's 1D, so we can go directly to experiment to macroscopic model without necessarily go to this kinetic formulation, etc. Okay. So let's start with a pedestrian. So let me just show experiments that have been done for study pedestrian here. So here's the setting. So the setting here is maybe sounds a little bit weird, like it's circular. The key idea behind that, it was to avoid boundary condition. So it's kind of cool when you circle because there's no boundary. I mean, if you think about it's 1D. So you don't have any boundary conditions, so it's easier. You remove one aspect, so that's inflow, outflow, etc. And so during the experiment, so we have I think you go up to 60 people inside this arena. They have different set of captors on the shirt and on the front hand as well. And there's a camera recording the motion. So let me just show you one experiment. So hopefully you can see the video. So you start just randomly assign a position, and depending can be like half of them move, let's say clockwise, half of them counterclockwise, is going to vary depending, and just we let them go for 2 minutes. So at the start is, oops, let me just replay that again. At the start is more or less like uniformly distributed, and quickly what you're going to see is start to have some lane formation. So you have like one group going to be inside, one group going to be on the outside, and more or less everybody kind of do the same thing except one guy. I don't know if you have seen this guy, but let me show you next here, kind of the same experiment, but now I'm just more like do the 3D reconstruction. Now I know what's the position. And so here you can see what's going on. So red moving in counterclockwise, blue clockwise. And quickly you have this kind of lane formation. And I think here's the blue kind of win. So because they're going to be inside, so it's actually going to turn faster. And so after, I think like, yeah, maybe 1 minute, it's almost done. You're going to see, let me speed up a little bit. You're going to see, yeah, that's it. So the blue are inside, the red are outside. So we have this lane formation. Everyone, well, almost. Yeah, this guy over there. And for some reason, okay, I can talk a little bit more about what happened with this, but he didn't want to be with the other group. It's doing his own thing, okay, fine. But as you can see, it's not very efficient because he was kind of inside. It was a lot of, let's say, friction with other pedestrians. But that's this kind of one individual. It's what happens all the time. You always have some fluctuation when you do an experiment. So we cannot just rule him out. It's part of the experiment. So as I say, we try to do fundamental diagram with that. So the first thing, we're going to have to estimate density. So we're going to actually project and only consider like the angular position. We're just going to forget about the radial position because we want to have like a 1D visualization. So what we're going to do, we're going to just average over like a area like this. So we average over R if you want. And so that's allowed to have like two distribution, one for rho plus, one for rho minus. And once you have that,
sorry.
Yes, go ahead.
There's a question from Ted that asks if lane formation can be related to tagging. If you saw the talk of...
I've seen briefly... Okay, I'll go back. No, I've seen briefly a talk. I haven't seen the full talk. So here, I don't think it's necessarily related to that. It's more like you're going to see it's more efficient if you want to go over lane. If you don't go lane like this one guy I showed before, you actually go slower because you're going to have a lot of friction. I'll come back to that, and you're going to see that the fundamental diagram help us understand what's going on. So let me just now show, so no analysis yet or no fundamental diagram here, just show what the distribution are. So here I'm going to try to represent what's going on, showing here, so color, it's the density. And here on the y-axis is the time. So let's say here, if you have a pedestrian moving right, it starts over there and moves to the right. Since time evolved, is actually moving diagonal like this. Rho minus, just reverse, you go on the other side. So you have here pedestrian moving this way. So the nice thing, because we do this kind of projection, it's only 1D, we can visualize the whole experiment with just here a 2D plot. If it was 2D, so we have 2D plus times 3D, it will be more complicated. So what you observe here, so basically there is so some lane formation here because you see there is some, if you want, concentration. The other interesting thing is that, so the slope here of what you see is basically the speed at which pedestrians travel. And when the slope kind of, I don't know if I should say increase or decrease here, but you have like the slope kind of change here. What's happening over there is that actually there is some, the other pedestrian coming on the other side. So that's why you kind of go slower because you have other people, other pedestrians going against you. So that's what you see here. If you just look at one panel on just one side, you'll see kind of the trace of what's happening on the other side. So there's an effect on rho minus, on rho plus. And so that's what we're going to try to kind of understand, try to model, if we can find a model that describes this kind of phenomenon. So here the question is, can we find some mechanism will be able to explain this dynamics. So what we're going to do, it's fundamental diagram, but slightly different version, because now we don't have one density, but two, because you have population going to the left, population going to the right. So rather than having one equation, we have just two equations. So here for rho plus, rho minus, it's kind of looks the same, okay, except rho minus is a minus because it's on the other side. And here, this f here is actually a function of two variables now, rho plus, rho minus. And so all the key here would be to try to estimate what is this f. So taking the data, we have to do some parameter estimation for this f. So something we're going to change is that actually this model, you see that it's a natural expansion for a system of the fundamental, let's say, traffic model, so lighting wizard. But there is actually a key difference when you have like a second equation, so now it's a system, that the model is no longer hyperbolic. So first, okay, maximum are no longer preserved. It's for those doing like hyperbolic system of hyperbolic equation is kind of normal. You know, when you have a system, it's no longer true, you preserve maximum. But more problematic, the model is not always hyperbolic. So here I refer to the post of Rabbi Ramadan, who already discussed this kind of same kind of concern for a different model, but also for a system where you can have different type of solution. So it's not as simple, let's say, as if you have just a 1D no system traffic model. And so here, so you can even write down what's the condition for the model to be hyperbolic. So we have some quantities that you can compute. And if I take an example of very basic flux here, you see I just write just a polynomial of order 2 here. So we just have like a, if you want, linear friction. So rho plus is, so if there is no, here if there is no counter pedestrian or no pedestrian around me, it's just one, if you want, is just my speed. And this speed actually decreases as rho plus and rho minus increase. So if you take this very basic flux, you have here this non-hyperbolic region, basically here in the middle over there. And this is not just like say, okay, who cares that it's non-hyperbolic? Well, actually, if you do some experiment, numerical experiment with what's happening, you're going to see it's very, very different. So if I start here with the initial condition inside the hyperbolic region, so here I'm not in this red zone here, but close to. So what do I mean here is that rho plus is roughly at 0.3, a little bit above. So this is the value that I put for the blue guys. And here for rho minus is almost the same, slightly less is the red one. And so I take like a uniform, I just perturb the a uniform state. And if you do some simulation, what's happening here, hyperbolic region, just gonna have some diffusion, everything will be fine, just red move left, the blue move right, and everything looks fine. Now, if I slightly change, so if I increase a little bit rho plus, so if I increase the density here, what's going to happen is that, okay, let me show you directly here, this small fluctuation that I just had to perturb the equilibrium just increase, and I start to have like this kind of, I want to call it jam, but okay, anyhow, so we have this kind of strange pattern here, where basically they reach kind of the maximum density, which is 1 in this model here. And it's kind of evolves, there's still some diffusion, but it's going to stick to some equilibrium like that, where there is like two blocks facing each other. So it's kind of cool if you mathematically, because you say like, that's interesting to have this pattern. But to be honest, what to be careful is that when it's non-hyperbolic, it's more like the model is not well posed. So here it's really a numerical solution. The true solution, it's debatable. What does that mean in this region? But it's inherent. If you have a bidirectional diagram, you're going to have this kind of region. So if you're in your experiment, you start to be in this region, okay, things can go bad. Doesn't mean that it's going to be as bad as the model here, but okay, you might have some strange phenomena. So let's see from a pedestrian, what do I have? So here, I'm just going to look at all the data points, rho plus, rho minus, look at the flux, and I'm going to do something very basic. I'm just going to here, just some if you want some histogram. So just regrouping all the value with certain value for rho plus, rho minus, and compute the average flux. So from a statistician point of view, it's not necessarily that great because okay, there's not like independent sampling. Okay, take all the points, and it's of course there's some correction in time. But here, I just do something very simple. I just put all the data points over there. So what you can observe in this experimental flux here, first, unfortunately, we don't have that much data points in very high dense region. And this is because of some safety concern. You're not allowed to put as many people as you want for your experiment. This constraint is going to be gone for ants. Ants, we can do whatever, so we're going to have way more. The density is going to go much, much higher. But even though we cannot have like very high density data points here, nonetheless, we see what's the effect of rho minus here. So rho plus here, basically it looks like we're almost in a free flow regime. So it's kind of increase and kind of just kind of plateau, but it doesn't really go down. We wish we should go actually to higher density, and we don't have. But for rho minus, it's kind of clear. I should have put actually what the color code means, but it's the red here is that you have high flux, blue it's low. So what you're going to see here is that rho minus increase, the flux always going to decrease. Okay, it's kind of normal because rho minus doesn't actually push you, it's push you on the wrong side. So the flux is going to decrease as rho minus increase. And so what we did here, we just tried to do like very simple equation formula for F describing this observation. So what do we do here? It's almost the same as a very elementary function I did before, except I have three parameters here. So A will be basically the free flow, the free velocity, sorry, so how fast you go if there is no one near you. B and C are going to be the two coefficients that's going to tell you about how much friction you have from your pedestrian moving with the same direction as you or those moving against you. So let's see. So here, just like I think that's what you get here from the experiment at 50-15. So it's kind of looks the same. You can do a bit more than just saying that it looks the same, but let's keep it simple here. But let me just show you how those three coefficients varies depending on the experiments. So first, we just look at the experiments where there is they all move in the same direction. So that gives you like, if there's, let's say that there's a basic model here. So we just have your own velocity and some friction from people moving with the same velocity as you. So here, 1.2, 1.3, you're going to see it's very consistent. It's always the same, almost. That's your like average velocity, and it's almost the same for experiment. B is relatively low, sorry, so 0.07. And of course, there is no C because they're all moving in the same direction. So now let's shift a little bit. So let's increase actually a little bit, people going in its opposite direction. So we're going to do like 75, 25. So here, very consistent, A doesn't change. B, almost the same. Okay, just some friction, but not so much. But that going back to the question of that add here, if you have pedestrian going against you, your friction actually you really penalize, so the flux really decrease. So C here is kind of normally it's larger than B. It's really like reducing your speed. So now finally we go like 50-50, and so something strange happening here is that actually A same thing, same velocity as usual. B increase and C, well, a little bit decrease is not very statistical, it's not very significant, but the key is that B really increase. what's happening here? Why B suddenly increased? That's lane formation. So what's happening, as we can see here, when you have lane formation, there's almost no interaction between rho plus, rho minus, because they have two different lanes. So actually rho minus, you don't care. You don't really have any contact with them. So that's kind of the limitation when you try to do project and just do things in 1D. You miss this information that actually, well, no, actually I don't see rho minus. So that's why it's more like big of the effect of this increase of density. Okay, we can do some R-square estimation just to make sure it's not completely off. But at the end here, as I said, so A angular speed is relatively constant, but the friction, surprisingly, actually increase when you increase the density. It's just because of this lane formation. So going back, just to conclude this part here, I just want to show you some comparison now, just some I-norm comparison if you want, experiment and the model here. So just to see if what's a major difference here will be if we start with the same initial condition from the model as the experiment. So it's not exactly same initial condition. I don't start at 0 because at 0 they actually they don't move. So actually I start at 3 seconds because I need to wait till the pedestrian starts moving. And so this is what you observe. So once again, left is experiment, here's at the model. So here rho plus moving this way, rho minus going the other way. And as we observe is that we also this kind of have this traveling band, and there is the effect of rho minus on rho plus. As you can see here, you can see that you can almost see the band here traveling as a rho minus here. So that's the effect of the interaction. But the model has an issue here is that it's kind of dispersed too much. It's kind of normal, it's a first order model, so it's more like what you're gonna observe here is a rarefaction wave, so it's tend to disperse, whereas for the experiment, not necessarily the case. So you have here some concentration and remain like this. So that's some limitations. So at one point we say that, okay, let's try a different approach a little bit. Let's try actually instead of having a first order, how about if we do second order? So what we try to do is just implement more like ORASC model. So again, I refer to the talk of Rinaldo for that. And so what the key in the second order model here, the key is that each individual has his own preferred direction, preferred velocity. So the additional quantities that you need to estimate, this comfort velocity, is not necessarily the same for everyone. We not necessarily go with the same speed everyone. But how do we estimate that? So here we have to go back to the experiment. And this is really now we go like with individual behavior. We recheck each individual and we see like the speed of the individual with respect to the density. And with that, so this is over time. So of course, like if there is no, so density is very low, then your speed increase. And if you regroup everything, what you observe, you have kind of a linear regression here, that as you increase the density, you reduce your speed. So what is your preferred velocity here? That's actually over there. So that's when there is no one, that's this guy here. Doing that, you can estimate for each pedestrian what is his own, which is preferred velocity. And you can do kind of the same framework, same analysis, where you now try to estimate not the fundamental diagram, but this kind of pseudo pressure, for those familiar with the ORASC model, is going to tell you like what's the difference between your velocity, your preferred velocity, and the velocity you actually has. So it's this difference here, this pseudo pressure. So we estimate that. It's kind of the same if you want as the bi-directional diagram. It's not F, it's P now. You do the same analysis, perform a comparison here, and what's happening is kind of reverse now. When you do ORASC, the solution that you have is not like a rarefaction wave, it's more like shock wave. So what's happening here is that it's kind of reverse, it's not dispersed at all. And so here, this is a simulation, so this is experiment. And so now we really have a shock if you want, and that's it, it's gonna stay that forever. Basically here, what's happening, there's no like, they cannot overtake if you want somehow in the ORASC model. So you're gonna have this kind of a shock wave just going forever. So pros and cons for the two different type of modes. But I must say it was a little bit frustrating when you do pedestrian because we could not really go like with interesting regime where it's super dense. So now we're going to be able to do that, not for pedestrian, but for ant. So let's switch to ant now. And so let's try to see what's their fundamental diagram when we explore that with various density regime. So setting is a little bit different because ants, of course, you cannot tell them just move around. Okay, you have to kind of need some incentive. So here, and pedestrian, we also need some incentive, but of course you have to pay people doing the experiments. So here's the money, here it's just like food. So what's the experiment? I'm going to show you a video in a bit, that you have a nest, you connect this with a small bridge to some food, and you got up the ants looking for food because you starve them for a couple of days. I don't know exactly how much time, but they really need food. So they're going to go after some time towards a food source, and then they're going to come back. So key here is just to analyze what's the diagram here, density flux, on a very specific region. Again, we try to kind of do things in 1D. So on here, just on this bridge. So they macrometed a lot of experiments, and so they vary the size of the colony to have like massive number of ants, but also the size of the bridge, because of course, if you're on high density, you can just reduce the size of the bridge in order to have higher density here. And combining all the experiments, what we end up having in terms of density flow points here, it's like roughly 500,000 points. So we have a lot of points, but not necessarily distributed uniformly. I'm going to show you in the next slide. But first, let me show you an experiment. So I'm just going to show you what's happening on the bridge. So let's see if that works. Okay, it's take a little bit of time to start. Okay, here it is. So this is just snapshot on a piece of the bridge here. And so I don't know exactly what was the density. It's relatively high density there. And what you can observe here, it's a mess, okay? But for those working with ants, it's kind of expected. It's not like the whole like very nice lane formation. So it's a little bit messy. So it's gonna be hard. Like if you want to do like basically agent-based models, that's hard. Like it's the whole doing like different things. So for instance, here you see what's happening here is go like on the sides of the bridge. So it's really messy. So that's why here using fundamental diagram it's almost like necessary here because tracking individual it's a mess. Okay, so despite this mess, can we try to see some fundamental law? Can we get some information about what's going on here? So let me show you here the data points. So here is like 500,000 points. So what's happening here, what you observe is that first, okay, you have this kind of free flow regime here. So as you increase the density, more ants on the bridge, you increase also the flux. But surprisingly, that will be the key observation is that the flux stays constant after. There's no traffic jam, so it doesn't go down. So basically here, if I may, here you have this free flow, but it's not really a congested regime here, like pseudo congested, because the flux remains constant. That being said, that doesn't mean like it's optimal in some sense. It's still bad to be here because you have more ants and basically for the same flux. So it's not ideal, okay? You have some congestion because it's not increasing anymore. So you have more ants for the same amount of work, but still there's no traffic jam. So what's happening here? Second observation I should say here is that, as you can see, I try to put in color here, we have way less points when we increase the density. What does that mean is that actually when the density starts to be very large, ants just stop going looking for food. So there's some self-regulation saying that, okay, there's enough people over there, I don't need to go there. So that's also kind of maybe something we cannot really like explain necessarily to human, because human, you have your own interest, you have to go. Here it's just and do everything for the colony, they don't necessarily have a self-interest. So they can do that because they don't have to go. It's all for the colony. Anyhow, so having those data points, let me just represent that a little bit differently. Let's forget about all the data points and just make the average here. So what you see in circle is the average. So you really see here like a linear increase, and then it's stay flat. And here in gray is the variance. If you try to fit your usual fundamental diagram with some usual function, you're going to be completely off. So if you use a very simple model I explained before here, when you have this kind of function like belt function, if you want, because you have so many points here in the free flow regime, you're just going to shoot up. You're not going to go down at all. So if you want to make actually something a little bit better, you have this another version where it's actually not two parameters, but extra parameters, where you have this power here. But unfortunately, in that case, you're going to shoot down way too fast. And so how can you describe what's happening here? And that's basically we end up with very basic ideas. You just shoot straight and just stay constant. So what we use here for that, if you just describe as simple as that, you just say, okay, just grow linearly and just stay constant. So in terms of parameters, you just have two. So it's as simple as the first one. And it's really kind of much, I mean, you can do some statistical analysis, etc. But from just the look of it, it's fit much better than the others. But now the real question is that how do we end up with such a diagram? So can we go back to the hand behavior, like what do they do, how's the interaction that explain this fundamental diagram? And so that's where it starts to be more difficult, because first experiment is a little bit messy, but also we have to be careful because you have so many parameters that you want you put in place. You're gonna have a problem that you might be overfitting. You're not really gonna explain. So for that, what we did actually, we don't necessarily go to a full 2D model. We just same analysis, just 1D if you want. But on a sub group of experiments, we analyze individual behavior, meaning we record for each of them the travel time. So we just on the bridge, how long does it take to just cross a section of the bridge? How many contacts did they have during the crossing? And what was the density? So the key is now, how can we play with these three variables here to explain this fundamental diagram? So it's kind of going agent-based model, not exactly, because it's still like I have a rough idea about what they're doing, but kind of a similar taste. So the problem here that usually we face is those three, of course, they're related. So if you increase the density, you expect to have more contact. If you have more contact, then your traveling time is going to decrease. If you decrease, you spend more time on the bridge, and it's a feedback loop, and that's why you might have like a traffic jam after a while. So what's happening here? How they relate to each other? So first, let's try to have some simple relation between the variable. We just explore how the density relates to the number of contacts. You increase the density, you increase the number of contacts, more or less linearly, okay? It might not be completely linear here, but there's so many, very few points over there. So it's more or less linear. Travel time and contacts, so this one is clearly linear. Variance, but it's really like more contacts, traveling time increase, because you spend some certain time when you have a contact, just bump into each other and kind of discuss. And so here we have like, it's affine because of course, even if there's no contact, you're going to spend some time to cross. So that's it. Travel time, even if there's no one. So how much time it takes to cross this portion of the bridge. And then it increases linearly with the number of contacts. Simple. But it's already nonetheless not so trivial, because if you just take these two information into account, what's happening here, so velocity is just the inverse of this traveling time. Here we're really describing actually this pseudo-congested regime, because if your flux here increase respect to rho, your velocity decrease in like 1/rho, you already capture the fact that when rho gets large, your flux becomes constant. So it's nonetheless already remarkable that the number of contacts only increase linearly with respect the traveling time respect to contact. There's no like feedback loop where you will expect something like to blow up. It's just linear. We've already explained this congested regime. Question now, how do we explain this free flow regime? So if we combine these two information, we're not going to have a free flow regime like this. It's always going to decay. So the velocity always decay with as you increase the density. Well, what's happening here is that there's another effect that we actually discovered doing this analysis here. If you just look at travel time with respect to density, and now we regroup for each, depending on the number of contacts you have. So if you just have 0 contact, super fast, 7 contact, super slow. And the difference between the curve here is that how much time you spend for each contact. That being said, here there's another effect. It's this curve. The fact that here, initially, when density increase, traveling time decay. What's happening here? So if we really kind of focus on this, so let me remove the contact and just look at what the traveling time without the contact. What we have here, takes the inverse, we have the speed. The speed is actually increasing as density increase initially. So what we thought was just a simple free flow regime, it's actually more complex, meaning that we have contacts that reduce your speed, but you also start to speed up. Why? It's because what we claim is because of pheromone. When we start to have ants, those ants always leave pheromone. So it's kind of direct the flow. Instead of wandering around, ants start to kind of move more straight in some sense. And so that's why the speed starts to increase. So the free flow regime is actually more a combination of two effects. Contact you decrease, but also pheromone you increase. At the end, they kind of annihilate each other, and we have a free flow regime. You combine that, put that into some formula for your velocity. So contact, decrease the speed, but kind of pheromone if you want, increase the speed initially, combine that, do some fitting, and what you get at the end, it's you recover this almost two-phase flow, so it's not as good if you want as what I showed before. The difference here is that there is some sampling issue. We didn't do this tracking for all the ants, it's too many. So we do a subsample, and we may have some bias where we select which ants actually we look at. So it's not as pronounced, let's say, this two-phase flow. It's more like a smooth version, but you really nonetheless get a rough idea what's going on. So we really recover these two effects here, this almost free flow, but again, it's more like a dynamic free flow. It's two effects compressing each other and just being constant. Okay, so let me wrap up now. So as a summary, so we discussed two types of experiments. So for pedestrian, we have a bi-directional model, and we have this interesting region, but unfortunately, we cannot really observe experimentally. Whereas for ants, we really went trying to push to the limit of traffic jam, but we cannot find them. There's no traffic jam. And so there is a very more like complex complex ways that they interact to mitigate this kind of decay of the flux. So they don't go if there's too many ants, but also avoid interaction. So at the end, we're resulting in much efficient the fundamental diagram. For future work, what we hope for would be nice is to have like a fully 2D framework. But for ants, it's very challenging because you have all those overlapping. Even if modern machine learning tool, it's going to be difficult. It's also because when you start to do 2D, you start to have way more parameter, boundary condition, etc. And so it's more difficult to interpret. What I really like with fundamental diagram, it's clear, everybody understands what's going on. So it's not necessarily like what's happening, but it's a cool tool to visualize. But nonetheless, if you want to go further, 2D framework will be will be very cool. With this, I'll stop there. It's 40, so I think my time is up.